Okay, so let's move on to the concept of magnetic fields. And just like we did for the electric field, we started with the concept of electric force. We're going to start with the concept of magnetic force. So we're going to pretend to do some experiments, and we have charged particles of charge Q naught, let's say, and it's moving, the charged particle is moving with some speed v, and it's in a magnetic field, but we don't, let's not discuss the origin of the magnetic field at this point because things are a little tricky there, unlike the electric field. So there is a magnetic field, and the symbol we normally use is B, and we start to do these experiments in the same way that we imagine doing them for electric fields and electric forces. And what we find is the following expression, that there's a magnetic force that behaves in this strange way. So it depends on the value of the charge. It also depends on the velocity with which the particle is launched and on the magnetic field that the particle is in this strange mathematical way. So it involves the cross product between the velocity and the magnetic field. So we want to get a sense of what kinds of things result from the cross product. So let's first point out that a force is a vector, so it has both magnitude and direction. And we can evaluate the magnitude, and when we do that, we get that it's equal to the magnitude of the charge. So the charge could be positive or negative, so the magnitude of that makes it positive. It depends on the magnitude of the velocity, right? That's the speed. It depends on the magnitude of the magnetic field, and it depends on the angle between the velocity and the magnetic field. So if the particle is moving with some velocity in that direction and the magnetic field at that point is pointing that way, then that's the angle phi that comes into play. And so we can notice that this force is maximum when V is pointing, say, that way, and B is pointing that way, so that this angle is 90 degrees. So we get V, so V cross B, these are perpendicular vectors, and then we'll get the maximum force because then we have the sine of 90 degrees, which is 1. So that's the most that this can be. And then we also have that the force is 0 when the velocity is sort of aligned or anti-aligned. Sorry, so the velocity could be either this way or that way, and the magnetic field is that way. So I guess we could say aligned or anti-aligned, because in that case we get, right, so that would look something like this. The velocity, the magnetic field is this way, and the velocity is also in that direction. Or the magnetic field is this way, and the velocity at that point is just opposite. Right, so this would be 180 or pi, and in this case the angle is 0. And so both the sine of 0 and the sine of pi gives us 0. Okay, so we have a sense of how to get the magnitude of the magnetic force. And the next thing that we want to do is to get a feel for how to get the direction, and this is where the right-hand rule comes into play. So more generally, we have the vector product of two vectors A and B, so A cross B equals C, and the right-hand rule says that if you take your right hand like this, and you put your fingers, your index finger, your middle finger, and your thumb in ways that they're perpendicular to each other, then you can find the directions of these three vectors. So this one is the index finger. This is your middle finger, and this is the resulting vector, which is, sorry, this is your thumb. Okay, so if the velocity is that way, and it's in a magnetic field that's pointing to the left, then the force is pointing upwards. If we switch the directions, right, the velocity is that way, so the index finger points that way, the middle finger represents the magnetic field, the magnetic field is downward at that location, then the right-hand rule gives you that the force is this way. So we'll be exploring these concepts.